right, so the neuron interacts with the muscle at the neuromuscular junction, or we could say this synaptic terminal comes together at the motor end plate. Notice that the motor end plate is highly convoluted. It's folded back and forth across itself. This should increase the surface area of the muscle cell where this neuromuscular junction is. This is going to help increase the signal to get the muscle to contract. So we have to imagine all along the surface of this membrane, there are all these receptors. And because we have lots of surface area, we have lots of these receptors. Now, in this diagram, the receptor that they're showing us is an acetylcholine, right? ACH, acetylcholine receptor, because of the particular type of neuromuscular junction that we're dealing with. All right, now, as the action potential spreads down along the axon toward the synaptic terminal, remember that the action potential triggers the opening of calcium channels close to the synapse. The calcium channels open up, calcium comes in, calcium binds to these secretory vesicles, what they're calling synaptic vesicles containing acetylcholine, that allows these to fuse with the membrane of the neuron. With fusion, the acetylcholine gets dumped into the neuromuscular junction. The acetylcholine is then picked up by the acetylcholine receptors. There's the acetylcholine binding to an acetylcholine receptor. In this particular situation, the acetylcholine receptor is basically an ion channel receptor. There's the acetylcholine binding to this ion channel receptor. So it's an acetylcholine gated sodium channel, or receptor gated ion channel, however you want to think about this thing. The acetylcholine binds to the acetylcholine receptor. It's a sodium channel, so with binding, we pop open the sodium channel. Okay? All right, now, we've popped open the sodium channel. What's going to happen to the membrane potential? Well, anytime we allow sodium into the cell, we are eroding the membrane potential and we're making it less negative, right? That should be depolarization, right? Taking the membrane potential toward less negative values, okay? As we do that, the action potential spreads along the membrane of the muscle cell, right? As we depolarize, that causes more sodium channels to depolarize, which leads to depolarization of more sodium channels. So this is going to help to trigger an action potential in the muscle cell. Okay? Before we talked about action potentials, we restricted that conversation to neurons. Well, now I'm telling you, well, you can spread an action potential along any membrane that has these sodium channels in it. The muscle cell has these sodium channels along the surface, and that depolarization here leads to further depolarization along the membrane. And that depolarization begins to spread down the T-tubules. So we're getting an action potential as more sodium channels pop open. In this case, not the acetylcholine sodium channels, but voltage-gated sodium channels are being triggered. They're opening up to spread the action potential down along these T-tubules. as that action potential spreads along the T tubules, we disrupt the resting potential of the T tubule membrane. And when we disrupt it enough, we affect the resting potential of the sarcoplasmic reticulum membrane. So this action potential is spreading from the motor plate along the membrane, down the T tubules, and then here, that disruption in the voltage triggers the opening up of calcium channels at the sarcoplasmic reticulum. The sarcoplasmic reticulum, like endoplasmic reticulum overall in animals, is a place where calcium is stored. So we're going to pop open these calcium channels that are voltage gated. That's shown right here. The voltage gated calcium channels pop open. Calcium comes screaming out of the sarcoplasmic reticulum into the cytosol, and now that calcium is what's going to bind to the troponin to pull the tropomyosin off of the actin myofilaments. Okay? So we're using the nervous system through acetylcholine-gated sodium channels to generate an action potential along the muscle membrane, which moves to the T tubules, which moves to the sarcoplasmic reticulum, which pops open voltage-gated calcium channels to allow calcium into the cytosol, and that calcium is what is ultimately causing the muscle contraction. Okay? I'm going to take a little break here, and then we'll come back for just a little bit more with muscles, and then move on to excretory system. See you on the other side.